Ramanujan for G is now available on the Google Play Store. Try it out for free.
Hi students. So last week we continued discussion on um, this is the class 11 class. So we continued discussion on um, collisions and momentum, right? Momentum conservation in the context of collisions, and also introduced the idea of the elastic collision, perfectly elastic collision, and the coefficient of resilience. And we did looked at some problems. We will continue that discussion today, but the related idea that we're going to introduce first is this idea called impulse. So, what is impulse? See, a lot of the related ideas in mechanics are quite related, you know. So, let me share my screen. So, for instance, right, the first idea is that of center of mass, right? When we apply Newton's law, right? Newton's laws, it equally applies to center of mass of a system of particles as it does to an individual mass, right? So if there is an external force that acts on a system of particles, right? Then too there is a net external force, right? The internal forces between them don't matter. And so the Newton's laws on the system of particles also work. Okay. So that is the critical point there. Okay. So the what happens is that the center of mass, which is defined as the weighted average of the, it's a point which represents the mean position of the body, you know. Typically it is like the centroid of the body, or the, if there are n particles, it is just the weighted average position of the mass, or mass weighted average, you know. So what we mean by that is mixi by sigma m. Sigma mixi by sigma m, is the definition of weighted average, right? So if there is one body here, there's one body there, then for this body this is the x, for that body that is the x, right? And so the center of mass is just like the position of a body is a vector, the center of mass is also a vector. It'll have a x, y, and z coordination, but it's a position, it's a position vector. Okay, so now if you have five different bodies, right, the center of mass of that system of bodies is given. So now, if you have the solar system itself, right? We all know that the center of mass is somewhere, in there, right? So now, in the case of the solar system, the sun is so big, right? And all the other planets are going around the sun in elliptical orbits. We will deal with gravitation shortly. Now, at any moment, the center of mass is potentially going to move, right? Now, what is the rule with respect to how and when the center of mass will move? The center of mass will move based on the external forces. Let's say the earth attracts the sun attracts the earth. The center of mass of that system is not going to be altered, because if there is no, if the if it was originally at rest, it will stay at rest if there's no external force, right? But if you take all the, the if you leave everything else out, like, Alpha Centauri, all the other stars, the center of mass of the solar system will, if it is moving at a constant velocity, will move at a constant velocity. If it is stationary, it will stay stationary uh, against the fixed stars in a inertial reference frame. That is how one looks at it. So when we understand n particles, a particle system with n particles, sigma mixi by sigma mi, will be the center of mass. So that is the x coordinate of the center of mass. Like that, you can have a y coordinate for the center of mass and the z coordinate. So the other way, if it is a continuous mass distribution, right, like a ring, a straight line, it is integral x dm by m, and n is integral dm, right? So integral x dm by integral m, right? So you take a small delta m at a distance x, then you integrate over that to get the center of mass. Later on, you will learn about moment of inertia, which is used in the case of rotation. And so that is also, that is another form. It is slightly related. That is integral x square dm. Okay, so by m. So, or there is not by m, just integral x square dm. Okay, so that is the center of moment of inertia, okay, about a particular axis. Okay, so or r square dm, okay, about a particular axis. Okay. So now you have sigma mixi by m is xcm, right? So now if you had three particles, you do sigma mixi by m by sigma m for to get the x coordinate, and sigma mi yi by sigma n for the y coordinate. In this case, you have three particles. At the origin, there is 0 0, there is 1 kg mass. At this point, at 1 comma 0, right, at 1 comma 0, there is a 2 kg. And then at this point, 1 by 2 root 3 by 2, the 3 points of a unit equilateral triangle, there is a 3 kg, right? So now, how do you find the center of mass? Sigma mi xi by n, right? So now, three objects are located on the x-axis as shown above. The center of mass is at, very simple, right? So it is 5 times 3 plus 2 times 10 divided by 10, right? 5 times 3 is 15, 2 times 10 is 2 times 5 is 10. So 25 divided by 10, right? 2.5. Very simple, right? So and so if you have a uniform rod, you have this simple integration that you do, right? And so at a distance, sigma mixi becomes x dm, right? So x, what is dm? Dm is just dx by L times M, right? So what is dm? Dm is, it's a infinitesimal mass of the at a distance x, right? So x times dm is m times dx by L, right? By m. So if you do the integration, you then end up with x dx integration is x square by 2. So half times x square by 2 between the limits 0 and L divided by L. So you will end up with L by 2. Okay, so that's how you need to look at this circular disk of mass m, radius r is initially stationary on an ice. Person of mass m stands on the edge of a disk. Without slipping, the person throws a large stone, right? So what they are setting you up to do a center of mass calculation, okay, at a velocity v. So if the ball is thrown, the man and the ball is what? Its mass is m by 20, right? It's thrown with a velocity v naught, right? Now, if the ball is going this way, the man and the disc are going to go this way, right? So why is that? Because initially the center of mass is at rest. Afterwards, also the center of mass be, uh, uh, you know, uh, will be this changing, right? Now, see, this will be true up until the point where it hits the ground, right? After that, other forces will change the mass, right? The the instance of action is only at this point. When he throws it, there is a um, uh, you know uh, conservation of momentum, right? So the momentum that he imparts is m by 20 times v naught. That is the momentum he imparts to the ball. So the the disk and the man with a mass of 3m by 2, total mass of 3m by 2, will move so that the momentum is conserved. They will move this way, right? There is conservation of momentum, and the momentum is mv naught by 20, right? Mv naught by 20 divided by 3m by 2 will be the velocity with which the uh, the man in the mass will move. Okay, so that's what's going to happen, right? Now, derive an expression of the length of time it takes, right? Now, if he has thrown it in a horizontal direction from a height h, right? So in the vertical direction, h equals half gt square. In the horizontal direction, t, therefore t is equal to 2h by the square root of 2h over g, right? So square root of 2h over g is the time, and so in that time, how much distance will go? V naught times t, right? So very simple, right? Now, the what they have now introduced another point though. There is a force. Okay, so when he chucks it, this goes with a momentum, and this moves with a momentum. But then that is the disc and the man move with a momentum. But then they introduce a friction between the disc and the ice. They introduce friction between the disk and the ice. You then have a net force. Okay, so then you have F equals ma, right? And so now, what is the A? A is, so what is the friction? Mu times m, mu times mg, right? Mu times mg is the frictional force, right? So now if you have an initial velocity, we calculated that initial velocity, right? It is mv naught by 20 divided by 3 m by 2, right? So that is uh, uh, you know uh, 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 so that is uh, 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 so mv naught by 20 divided by 3 m by 2 will give you mv naught by 30, right? So mv naught by 30, right, is going to be the or v naught by 30, right? V naught by 30 is going to be the initial velocity, right? Now it is experiencing the mass is 3m by 2, right? And the force is 3m by mu times 3m by 2 times g, right? So now it has a initial velocity v naught by 30, right? So v naught by 30, that is the initial velocity. It is decelerating at this rate, right? Uh, um, mu times g, right? It's decelerating at a rate mu times g, and therefore, what is going to be its, derive an expression. The time it will take for the disk to stop, right? So it will stop when v square is equal to uh, your the time relationship between time and acceleration is given by v is equal to u plus 80, right? So v is 0, u is v naught by 30, and therefore it is that is equal to 80, right? So a is mu naught g, right? So it's very simple from that point of view. You can calculate now. So this is a very simple problem, right? Now, there is also this concept of center of gravity, which is typically the same as center of mass if gravity is uniform. If it is non-uniform, then you will have sigma, the different varying gravity coming into picture. Otherwise, it will be the same center of mass. So typically, you hang a body like this, it will go through you tilt it, hang it, or the intersection point of all those lines, right? When you hang the body, you draw a straight line, that those lines, the intersection point of those lines will give you the center of gravity, right? And so, so it is. the when you draw when you hang it from a roof, right? Just extend that line, you will end up with the center of gravity, right? So we derived all these simple laws. We finished this problem as well. So now we'll discuss impulse. Impulse is the result of is what happens when a cricket ball is hit by a batsman, right? So the ball or a baseball is hit by a batsman, right? The ball is coming with a momentum, right? Now the bat comes and hits it for a brief period of time, Ti to Tf. Between the times Ti and to Tf, there is a force applied by the batsman on the ball, right? Now, based on the force he applies, right? Let's say he applies a constant force of F, right? So F times dt will lead to a change in the momentum of the ball. Okay, so Pf minus Pi, dP by dt equals F, right? So if you write dP equals F dt and integrate over a short period of time, you will end up with Pf minus Pi. The difference between Pf minus Pi, which is integral F dt, is what is called impulse. So you have an impulsive force, that is a force which acts over a strong short period of time. Like when a ball hits a wall, we already looked at the problem from Wikipedia or from Khan Academy, right? When a ball hits a bat, when a ball hits a wall, etc., etc. There is a short period of time when it makes contact, and there is an impulse, and the net change in momentum is FDT, integral FDT. So we already looked at this. So a ball of mass m falls vertically, right? Hits the floor with a velocity vi and then rebounds with a velocity vf. So what is the magnitude of the impulse exerted by the floor, right? The floor has changed the momentum by how much? Initially it was m times vi, but it is now minus vf, m times minus vf, right? So so the change in the momentum is m times vf, which is the final momentum, negative m times vf, or positive m times vf, minus m times vi. So the minus and minus will become a plus. So it will become, so what is the force? It is m times vf plus vi. If you wrote b m times vf minus vi, you have missed the idea of the change, the direction. M times vf plus vi c. Okay, so now right? So if you, when you integrate, the body is moving in a straight line along the x-axis. So the F versus T, the net force Fx is given like this. What is the, which of the following could be the Px of the object as a function of time? Okay, so the, here is the thing. Okay, when you have this kind of a line, right? Fdt is what? FDT will be, is the area, right? And this is a increasing value, right? So it is continuously increasing throughout the whole journey, right? So it is increasing at a fast rate, then it is increasing at a steady rate, and then it is continuing to increase but at a slow rate. So this is probably what it is, because this one, it's definitely not this one. We are trying to find the area under this. The area under this will is going to give you the momentum, right? So we can only say that PF is greater than PI, and in this case PF is greater than PI. This is not like that, this is not like that, this is not like that, and this is not like that. So only E satisfies that, because the area under Fx versus T will give you the impulse imparted, and the impulse is the change in the momentum. Okay, so I'm not going to do every problem. I'm going to try and help you little bit move on here, so that you also get an idea of how problems are attacked. Okay? So there are three types of collisions. We already this is a quick review. There's inelastic collision when only momentum is conserved. There's an elastic collision in which momentum and kinetic energy is conserved. Right now, in the case when both are conserved, you end up with a coefficient of restitution, which is the change in the final velocity, which is a change in the difference in the velocities, final velocity divided by the difference in the initial velocities, right? Difference in the final velocity divided by the difference in the initial velocity as -1, right? And therefore you have v1 minus v2 by u1 minus u2 equals -1 for a elastic collision, and for a perfectly inelastic collision you have it as 0. And what does it mean that it's 0? The two bodies stick to each other and have only one common velocity, and anything in between, it has a e between 0 and 1, but not 0 or 1. Right? So partially elastic, nearly elastic, right? Collisions between two ivory balls, steel balls are is nearly elastic. Okay, so remember that, and then we derive the equations, right? And we use those equations. Okay, so then oblique collisions, we said that if you have equal masses, you have perfectly elastic oblique collision, then they will move at 90 degrees. The angle between the two bodies will always be 90 degrees, but it's only true for oblique collisions. Okay, so and then we explained what happens. We explain how this formula is derived. You take this one and you plug it into this one. This is also true, but typically you need only this one and this one. You solve for v1, you write v1 in terms of v2, and then you plug it in there, you will end up with a v1 equation. You write v2 in terms of v1, plug it in there, you end up with a v2 equation, right? And therefore when you plug in particular values, you end up with these other results, and they are worth learning too. Okay, so now let's look at this one. Or I think we already looked at this one. Block of mass m is moving the velocity v in the horizontal direction. Block 1 makes an elastic head-on collision, right? Which of the following are correct with respect to v1 and v2 for blocks, respectively, immediately after the collision, right? So this one is a direct application of these two. Okay, now you can either use this one, or you can start from here and use this one and this one. Okay, either way you reach the same answer. In this case, I used, I am little lazy. I mucked up the formula. I plugged it in. Therefore, I got V1 equals M1 minus 2M times, right? V, right? And U2 is 0, right? Because the second mass is at rest. So U2 is 0. Therefore, I ended up with this one, just the first part for the first one, and just the second part for V2. Okay, therefore I ended up 3m the denominator, and the numerator I ended up with this. So minus v by 3 and 2v by 3b, right? So notice how they've given you all very interesting answers, right? Why do they do that? Very similar answers, so that you don't make any silly mistake in the calculations. If you had picked this one, you had done this calculation and picked this one, unfortunately they were said sorry, one negative 1/4 mark in the JEE, right? Anyway, remember oblique collisions, there is always conservation of momentum, and then if it is elastic, then you have perpendicular, mutually perpendicular. Right? So then we looked at these problems, but then I have to move on, right? So today I am going to quickly discuss potential energy, right? See, this is a very important idea. Okay? Potential energy is defined as the capacity of a body to do work. When do we define potential energy? In a conservative field, which is caused by a conservative force. What is a conservative force? A force that is dependent on the all other things being equal, dependent essentially on the position. So gmm by r square is a conservative force. What is gmm by r square? That is the force of gravity. According to Newton's law of gravitation, the uh, a force of attraction due to the gravitation force exists between any two bodies, any and every two bodies. Every body attracts every other body with a gravitational force g times capital M times small m, where capital M is the weight of one body and small m is the weight of the other body. G capital M small m, the product of the two masses, divided by the square of the distance between them, gmm by r square. And r is the distance between the bodies, right? So when you have such a force, then the you can think of it that one body has a field around it, and any other body brought into that field will experience the force, right? So that is called a conservative force, right? Therefore you end up with f of r, right? And therefore, because you have for f of r, therefore you have a potential energy, right? Defined for that. And the associated potential energy is gmm by r, right? It is the work done to bring a body from infinity to that point in the uh, in the first body's field. So if you have a unit mass, right? So then you can define a potential. So gmm by r will give you the corresponding work done. So how is the work done? What is work first, right? So we defined potential energy, right? Is the energy gained by virtue of a body's position, right? So in the context of, say, the earth, right, we define potential energy. Potential energy is the, typically when you calculate potential energy, it is the m times g times h. Why is it m times g times h? It is the work done to move it a distance h. What is the work done to move it a distance h? Integral f dx is the work done. Work done by a force is f d cos theta, right? F dot d. Okay, so work done by a variable force is given by integral fx dx, f of x dx, right? It's a variable force, varies with distance, right? So now, why do we say it is mgh? We say it is mgh because the distance for small distances, the mg is a constant. From here to even Mount Everest, the gravity does not change much. Almost at every point on the Earth's surface, most points on the Earth's surface, gravity stays almost the same, right? Because the Earth is almost a sphere. Okay, so we just say 9.8 meters per second square. So now if I have to move it from here to here, I assume the force is constant. It is not an f of x but a constant f, right? So it becomes mg times h. That is the work done to move it from here to here. Now when I do work on this gains that amount of potential energy, and it can then do some work for me, right? So let's say you push, there is water at a height, it can then drive a generator. I don't know if you have seen this movie Swadesh, right? Swadesh, the hero, Shah Rukh Khan, um, uses water to generate energy in the form of electrical energy. Okay, but how does water produce electrical energy? From a height, when water flows down, it is continuously using up energy. And when you put a generator in the middle, that electrical energy, that mechanical energy, right, potential energy of the water partially gets transformed into, it then causes the generator to rotate. When the generator rotates, it gets converted to electrical energy, right? That is called through a process called electromagnetic induction. You will learn that next year, right? Now, so f of x dx is the work done, and that work leads to a change in the potential energy, right? So when I lift it, I increase its potential energy. Then when it drops, it loses potential energy. And when it and typically if you leave a body, right, the the potential energy declines and its kinetic energy increases. It starts moving faster and faster and faster. So if its potential energy goes down by mgh, its kinetic energy goes up by delta half mv square. Kinetic energy is half mv square. Initial kinetic energy is zero. It will be at what speed? It will be delta h times mg will be the will equal half mv square, right? So the kinetic energy gained is the potential energy lost. So there is a conservation of energy due to a conservative force. Okay, so that is the idea behind work energy. Okay, so work energy theorem says that that there is work done, right? And then we discuss this idea of g negative gmm by r as the potential energy or mgh as the potential energy. So now we quickly introduce the various we quickly introduce gravitation. I have always been talking keeping you at the edge of gravitation when I introduce potential energy and kinetic energy, right? So the Newton's law of gravitation is gmm by r square, right? And the first person who dealt with this was this guy called Tycho Brahe. Tycho Brahe, and later his student was this guy called Kepler. Kepler introduced three laws, right? The first law is about planetary motion. He said that the sun is heliocentric theory. The sun is at the center of the planetary systems, and all the planets revolve around the sun. Earth revolves around the sun, right? And then at the same time, the earth also rotates while revolving around the sun. You all know that it takes 365 days to do one revolution for the earth. But other bodies, they have a different year, right? Now, how is their year related to, and so for that, Kepler said it is given by this law: T square is proportional to R cubed. So why is t square proportional to r cubed? That is got by writing m omega square r equals gmm by r square. Okay, so if you cross multiply, the r cubed goes to the other side. The m's will cancel, and therefore gm is the in the case of the solar system, the mass of the sun, right? The cancel though, that is the planetary mass, right? So gmm by r square equals m omega square r, and omega equals 2 pi by t. Therefore, t square is proportional to r cubed, right? The r square joins with the omega square r, the second r, right? So it becomes r square times r cubed, and omega is what? 2 pi by t. Therefore, you take the t to the other side, so you end up with t square. T square is therefore proportional to r cubed. That is Kepler's third law, derived from gmm by r square equals m omega square r. The second law states that the is derived by saying that the angular momentum is conserved. Angular momentum is mr square omega. Mr square omega is conserved. Another way of saying that is that the area covered by the planet, right? R square times omega is what? The area swept in a given period of time is a constant. R square omega equals constant is same as saying that the area swept is a constant. So that was Kepler's second law. It is the conservation of angular momentum of planetary bodies going around the sun. So when it's closest, it will go fastest. When it's furthest, it will go slowest, in such a way that the total area is the same. Why is it area r square delta t? R square dt. Okay, therefore that is r square theta, right? R square d theta by dt, right? R square d theta by dt is the area, half r square theta, right? Pi r square gives you the What is pi? 2 pi r, right? Circle is how many radians? Remember, this is in radians, right? Circle is how many radians? 2 pi radians, right? Pi radians is half a circle, right? It's 2 pi radians, right? So half r square theta, theta is in radians, gives you the area. Therefore, and half r square d theta by dt gives you the area covered, the rate of area coverage, right? Half r square theta is the area covered when we go through an angle theta, right? And the ellipse is similar to the circle, same story, basically. That is, I mr square d theta by dt. If mr square omega is the is I omega, or it is the angular momentum. Angular momentum is also conserved. Okay, so those are the like Kepler's laws, and you will get questions about Kepler's laws. Okay, because you are expected to learn that. And Kepler's third law, T square is proportional to R cubed. We derived that, right? GMM by R square equals M omega square R produces, and omega equals 2 pi by T produces. T square is proportional to R cubed. Okay, so now near the earth you can also derive this, that as you go a certain distance, you can rewrite, like if you go a distance h from the earth, you can write 1 by r plus h the whole square. You can rewrite this approximately as 1 minus 2h by r. Okay, so that is just when you do a expansion, you can drop the second term, the later terms. Okay, therefore you have 1 by 2h by r. That is just a Taylor series. Okay, you will learn about that. Okay, so now where is the gravitation? So inside the earth, what happens to the gravitational field? It is actually linear. At the center of the earth there is no gravitation. Okay, now as you go up, it goes up linearly. G equals G naught H G naught by R. Okay, so at the center of the earth, it is 0. At On the surface of the earth, it is little g, 9.8 meters per second square. In between, it is linear. It increases linearly. Okay. The reason for that you will learn later, when you will understand later when you look at Gauss's law. Okay, right now I think if I go too much into that, it will, and beyond the after outside it follows gmm by r square. Therefore you have, this is just gmm by r square, right? What is this r? That is the radius of the earth. Capital R is the radius of the earth. Now after r, it is going to go 1 by r square, right? It's going to decline at the rate 1 by r square. Inside it is at the center of the earth 0, straight line till g, and then declining from there on. Okay, so that is how that is all the details of gravitation. You'll get a lot of questions dealing with gravitation, but you must, if you understand the basic theories there, right? Basic theories in gravitation are all these. There's not that much more. You must understand 2 pi by t period, right? What is the period of the earth, of the earth? 1 year, right? So you understand that is the, and that was, therefore you have 2 pi by t equals omega, right? So you understand those things. So what is 2 pi? 2 pi is the time it takes to go one round in radians, right? 2 pi is one full circle, 360 degrees, right? So that's what they are telling you, right? So there, I will not go into the details of rocket propulsion because we've already gone there. But then work energy theorem is a very important one, right? So the work done by a force on a body is equal to the change in the kinetic energy. Okay. Now, work energy theorem, right, is, so I do, let's say I do a piece of work, right? So now sometimes you get very confused with this kinetic energy and potential energy, right? If only I was the actor, right? See, now when I do work, right, there are two forces. One is my hand and the other is the earth. Okay, so that is where you have potential energy and kinetic energy. When I do this work, right? I'm increasing the potential energy, right? There's no conservation there because I'm the actor. If you drop this in the conservative field, there is no, my action is not there. Only the Earth's action is there. When only one force is there and it is a conservative force, then you have conservation of energy. When I do work, I actually do increase the energy, right? So you must note that aspect. You can get very, very confused for no reason because you don't know the difference between my doing work and the earth doing work. The earth is a conservative field. Its work is conserved. It's in the conservative field. There is conservation of energy. Okay, so that's how you deal with it. That's where you introduce potential energy. When I do work, there is no potential energy. Okay, except if it is to increase the energy of the body, right? So that's the idea there. When I do work, it changes the kinetic energy essentially. Think of it that. Okay, so so don't get confused by this idea of potential energy. It is defined only in some cases, case being when there is a conservative force, which is typically gravity or some kind of electrostatic force. Okay? Otherwise, it is not defined. So the work done is the change in the potential energy, right? When I did work, it led to right? It led to a change in the potential, right? I did work on the body, and its potential energy increased. Now, when the body does potential energy, its when the body does work, its potential energy decreases, right? So that is the idea there. Okay, so who does the work, who gains the energy, those are always very, very important. That is a very central idea, not just in this field. When you go to thermodynamics, etc., also work and energy are two sides of the same coin. One leads to another. Okay, and you must understand that how they change, how they interoperate is essential to your understanding of so many things, because energy is such a central idea in physics. Okay, now if k equals half mv square, the rate of kinetic energy is F times V. dk by dt is F times V. Rate of kinetic energy is called power. F dot V is called power. F F dx, you know, is work, right? Now, rate of work is power. dk by dt is power. Okay, so that is how work energy theorem translates to power conservation, power actions. Okay, so it can also be derived, is also an integrated form of Newton's second law. See how he derives it. mvdv, mdv by dt equals, right, and he introduces dv by dx times dx by dt. Dx by dt is v, therefore mvdv by dx. So f dx equals mv dv. Therefore, you integrate both sides, you end up with integral f dx equals delta mp, half mv square. Delta half mv square. Okay. So now, when a body is in circular motion, right, the force is radial and the body is moving tangentially. So the work done is zero because f dot v, right, or f dot d, right, delta d, right, they are f, they are perpendicular. Okay. So keep that very much in mind as you go about solving these problems. Okay. So then cross product becomes very important to understand when you look at rotation. Rotation is always dealing with cross product. Okay. Now, for that, you must understand all the terms. Omega is a vector, right? Torque is a vector, right? Angular momentum is a vector, right? And all these terms are related. And finally, moment of inertia is a scalar. Okay. So all these terms are, in fact, it is a tensor, but we always say it's a scalar. Right? Now, the average angular velocity is d theta by dt, delta theta by delta t. So now angular velocity is a vector measured in radians per second. We already said omega equals 2 pi by t, right? If you have a constant angular velocity, a given period, right? Instantaneous angular velocity, right? Now, the velocity is given by omega cross r. V is the tangential velocity given by omega cross r, right? So, um, so remember that one. V equals omega cross r, right? And then when you look at A equals what? Omega cross r, omega cross V will give you one kind of A, right? That is the AR. Alpha cross R gives you the other velocity. Now, a body in uniform circular motion has only a radial acceleration. It doesn't have a tangential acceleration. That is the uniform part of it. If it is going fast and fast and fast and faster, it will also have a tangential acceleration. Also, and the rate of tangential acceleration is called angular acceleration. That is called alpha. And the tangential acceleration, the linear value is alpha cross r, where the angular acceleration is d omega by dt. Alpha cross r is at, and ar is omega cross v, and v is omega cross r. Okay, so learn these cross products. That's why I said rotation is full of these cross products. So once you learn these cross products, a lot of these things become easy. The equivalent of linear momentum in rotation is angular momentum, and dl by dt is tau. Just like dp by dt equals force, dl by d equals tau. Tau is the torque. Torque is the moment of the force, and the moment of anything is r cross f. The moment of the momentum is angular momentum, r cross mv. The moment of the force is r cross f, torque. Okay, moment of the force is the torque. So similarly, there is also conservation of momentum when there is no torque, right? So those are the ideas. They are very parallel to what you learn in right now. The angular momentum, just like the linear momentum is m times v, the angular momentum is I times omega, where omega is the angular velocity. So the angular momentum equals the moment of inertia times the angular velocity. Moment of inertia is r square dm, just like we looked at center of mass, r dm by m, right? Here there is no denominator m, it's just integral r square dm. Okay, so those are all the ideas that we look at in the context of rotation, and I introduce all these ideas very, very quickly so you understand all these ideas very, very quickly. But I'm going to little bit stop here so that you get an idea of how to understand these ideas and their relationships. I went very fast today, I know. I went very fast, so because this is a preparatory class. Okay, you should now, and I want to introduce gravitation, I want to introduce energy, right? And then I want to introduce you to all the rotational ideas, right? So this is pretty much the bulk of mechanics. If you got all this, you have to then do all kinds of problems. Now, typically our students at this stage, that is, if you have spent the first semester listening to my lectures, then today's lecture would not have been so complicated. Okay, but if you didn't listen, you should get our app. Okay, then you should learn chapter by chapter, chapter by chapter, chapter by chapter, and then solve problems in a certain order. Okay, so so before I go, let me introduce you to our two apps. Okay, we have actually more apps. So let me introduce you to all our apps. Okay? So our first app is Ramanujan for JEE students. Okay. Now, if you have had Ramanujan for JEE students, then we also have dot Sushruta. Okay. So this is our NEET app. Okay. Now, our NEET app is available for students. Okay. And you can see it provides you everything that you need, and we have integrated it and produced a fantastic app. Okay. So work with our NEET app. Okay. Home.nyanmarga.sushruta. We have added more products. Okay. Most recently, we have added our CBSE and JE apps, and our CBSE and JE apps along with our AP list of AP apps. Okay, so you can contact us. I am Srini at jnanamarga.in. Srini at jnanamarga. IN if you want to know more about our CBSE, and we also have a GSEB for Gujarat State Board or State Board apps, or so you can contact us if you are interested. I am Srini at myanmarga.in, or you can contact developer at myanmarga.in. Okay, and we will help you with the programs that we have. Okay, engagement myanmarga.in. So please contact us. We'll be able to help you with apps, getting access to our apps. With that, I'm going to stop for today. My advice to you is download the app and work hard, and keep studying. Study from the apps, you study from the textbooks. For physics, we have always, for class 11 students, part 1. For class 12 students, part 2 of HC Verma. I recommend HC Verma for students preparing for NEET or JEE, because you need a little more than just the NCRT textbook. If you are preparing just for your boards, you can manage with just studying well from the NCRT book. The NCRT books are come integrated with our apps, and then we overlay it with very good videos. That is, if you want to conceptually understand the details. So very useful, and you can learn well, and then you can do very well and prepare yourself for success in engineering, in medicine, and in sciences. Okay, so we also now have our IT certificate. Is if you're interested in IT education, contact us. All right. So with that, I'm going to stop for today, and see you all again next week. If it is Saturday morning, you're with me for physics, but then we also have a very good series of lectures with Professor GK Bhatt for biology, Professor Tiwari for chemistry, and Tarun for maths. So please attend all our lectures and